Share screen. Can you see my screen?
Yes.
Awesome. Perfect. Thank you, friends. Welcome to Deep Learning Adventures, a fun and engaging meetup where we talk about deep learning and data science in general. My name is George, and I'm joined today by many friends around the country and around the world. And today, David and I, as well as my co-organizer, Robert, are going to take a deeper dive into feature engineering. I'll be covering the first two sessions of this feature engineering course from Kaggle, and David will be tackling the third and the fourth one.
George, the font's pretty small. I don't know if you can make it bigger.
Yeah, I can zoom in a little bit.
Looks good.
Perfect. So this is, to me, the third session that these Kaggle Mini Courses are taking a deeper dive into machine learning. There was an introduction to machine learning course that we have explored together as a group. And there was an intermediate course as well. To me, this is a continuation of that course. It builds up on them. So if encodings is something new to you, or if categorical variables or numerical variables are something new to you, I encourage you to check out the other courses on Kaggle as well. Today, Kaggle is having a little bit of server issues, so fortunately I have all the notebooks open, but I'm curious if you have any issues with Kaggle and opening notebooks. I know it's kind of slow. I think it's getting overwhelmed today. Cool. So today we'll be building a baseline model, and then through different iterations, we'll be enhancing it. We'll be adding more and more features to it, and we'll see how that impacts performance. Robert, if you don't mind, you can share the links with everybody for our Slack maybe, or our recordings. That'd be great. Thank you. Cool. So for the baseline, I'm not able to open the tutorial notebook. Let me see, maybe I'm today. Oh, yeah, I get this error. But I'll be working with the exercise version of it. So let me zoom in a little bit. They cover the same topics, and just I think they focus on different data sets. So the course focuses on the Kickstarter data set. So you have data sets from the Kickstarter challenge, I think. It had different features, for example, what category your project was being released on, what date, how many people were supporting it, what was the goal they were trying to raise, and things like that. And then in the end, you had a target column, which was basically if the project was successfully backed up, was basically able to raise all the money they needed to launch that Kickstarter project. That was on the theoretical part of the Kaggle Mini course. On the exercise part of it, there's another data set that I'll explain right now. So this data set is actually an ad tracking data set. It contains several features, as we'll see soon. And the goal is basically to detect if somebody who clicks on an ad actually installs an application that is being advertised on an ad. And most of the traffic that we'll see is basically people not installing or downloading the app, just clicking on the ad. And there are very few cases where people actually click on the advertisement and actually install the application. So that's the stalking data ad tracking fraud detection challenge. I think it was run a couple of years ago, and you can still submit to it even though it's closed. So when I was doing this exercise, I'll be talking about a modified version of this data set, because the original data set of this Kaggle competition is about, I think, 7 gigs in size, has about 150 million records, and it's very, very imbalanced. 99% of the data is basically records of people not downloading the application, and less than 1% is records of people actually downloading the application. So this notebook here in the exercise actually uses a modified version of that, which is basically a balanced data set, a balanced version of it. Instead of 150 million records. It contains, I think, about 2 million records. Cool. So this is the exercise part of it. So there are some prerequisites that you have to execute as part of Kaggle to make sure that the results you're getting are as expected. So you just simply execute that. And for our baseline model, we'll be building a machine learning model, a tree-based model that will take several features as input. We'll calculate a tree-based model, and we'll be able to do prediction based on if somebody actually installed an application or not. And looking at our data, we have, these are the fields. We have IP, which is the IP address of the user. App, this is an application ID for marketing purposes. I think maybe this could be maybe which website somebody came from or which email marketing campaign and things like that. That's another ID that we have as a feature. The device is the device type ID. Could be you have an ID for each phone type, for example, iPhone or Android or different devices or Samsung or Huawei. You have another ID or another field for the OS version of the mobile phone. Another one for the channel. Again, this is something internal, I guess, to the ad publisher. The time of the click that somebody clicked on the advertisement. And then if somebody installed the application, there's an attributed time as well. So if user downloaded the app after clicking on the ad. And the target variable that we're interested in is called isAttributed. So the target that basically it's 0 if somebody did not install the application and 1 if somebody installed it. And for privacy purposes, IP, app, device, OS, channel are all encoded, as we'll see. They're not the original values. So that's the training data set that we'll be working with. And then the test data set has 2 extra differences. One of them is it has a click ID, which is used as a reference. It's basically an ID that will allow us to keep track of different records. And obviously the target is not included. It's our job to predict it. Great. So we'll start with importing the training set. And again, this is from this feature engineering data set in Kaggle, which is not the competition data set, okay? This is just the balanced version of it. We'll be reading this train sample.csv. We'll be parsing the dates, the click time dates, and they'll be storing all these records in this click data frame. And let's inspect it a little bit and see how it looks like. So it has about 2 million records, 2.3 million records. Has 8 fields, as we saw: IP, app, device, OS, channel, click time. And then this is attributed is 1 if somebody installed the application, or 0 if somebody did not install it. Cool. I have some code here that actually works with the competition data set. I will skip it for now, and then maybe we can cover the competition in the end. Awesome. So one thing that we'll be doing as the baseline model is on top of the original features that we saw, we'll be creating some additional features from click time. Specifically, we'll be trying to extract the day, the hour, the minute, and the second. Instead of working with daytime fields, we want them stored as numbers. So from the click time field, we'll be extracting, we'll use this DT accessor, what is called in Python. We'll be converting that to day. We'll be storing that as a unsigned integer in a new field called day. We'll do that for the hour feature, for the minute feature, and the second feature. Now when we look at our data, now we should have 4 new features. So the day should be 6, the hour should be 15, the minute should be 13, and the second should be 23. So basically, we were able to parse out this information from the daytime, because it's easier for us to train models that works with numbers compared to daytime objects.
And George, is it fair to say at this point, this is actual feature engineering as opposed to data preparation?
Yeah, I would say so. Yeah. Yeah, I don't know if there are any models that can work with datetime objects out of the box. So for me, yeah, this is between feature engineering and pre-processing. So I don't know.
Yeah, it's a hard call, I guess. I don't, since we don't have access to the tutorial part, I'm not sure if they stated that one way or the other. I can't remember.
I don't know. In my opinion, engineering would require a bit more creativity than just pulling numbers out of the date.
And parsing it. Okay.
But I'm sure that's open to debate.
You can change the calendar or the day, or the format, something like that.
Yeah, the only thing I would say is a lot of times when you process data, you don't end up with new columns. You just end up with new numbers in the columns. And to me, this seems it's the easiest form of feature engineering if there ever was one.
Yeah.
Yeah.
But our doesn't seem like a crazy feature though, because behavior could be different at different hours of the day. So.
Oh, absolutely. Yeah.
Yep. Awesome. I'll skip to the competition one. Then the other thing we need to do is all the different IPs, the channels, all these different fields. They are somehow encoded. The hours and the minutes and the seconds, they're not. They're just encoded by their numerical value. But our goal would be for these categorical features: IP, app, device, voice, channel. We would love to encode them using our own encoding process. So I'm not sure how they were encoded originally. So I don't know what kind of encoding scheme this competition used, but I think, for example, the minimum value of IP or the maximum value of IP, I don't know what it is. It could be some huge number. And if we use our own encoding mechanism, let's say for some reason that IP is very popular, then if we encode it on our own, then probably that will have like a smaller value, let's say like a 0 or 1 or a 2. So did you understand, David, why was this needed? I mean, that's my understanding, that basically we were unaware of the original encoding of these categorical features.
Yeah, I think because we don't know what encoding method, we can treat these just as categorical strings in a way to us. It's the same concept, right? So that's why you would want to encode them as numbers.
Mm-hmm.
We don't know what they used. So there's, if you look at that, go back to IP up there, what I mean by this is, we don't know that 5744 versus 119,000 something has any relevance as far as the difference between those two numbers, right? It could have, so our model may perceive that there's something to do with that, but that's not, we don't know that because we don't know encoding. So
is there any harm in encoding an already encoded feature? I don't think there is any harm, right? In terms of modeling.
Well, if you lost meaning, if the encoding had something that you could learn from in it, and you took that away, you might lose.
Got it. If it was some kind of ordinal.
Exactly. If there was some meaning to this.
Okay. Awesome. Okay. So in this exercise, we use this label encoder, and question number 1 that I have from the previous course, Kaggle Mini Course, if you look at the documentation for scikit-learn, it says that this pre-processing label encoder is supposed to be used for the target values and not the input. So in the exercise that we use on the input, I use it for the input as well, but I'm curious, do you usually use it for the input or just the output, David?
I only use it for targets, but I wonder if possibly the reason they're doing this is because if you just use the basic sklearn pre-processing encoders, ordinal encoder, which is what I would normally use, it doesn't handle unknowns or new values, right?
Mm-hmm.
So if you're in your test or in the real world, you encounter new values, it'll actually throw an error. Whereas label encoder, you can specify a value for for unknowns, or you can specify the behavior. But if you get the sklearn contrib, contributed, there's an ordinal encoder in there that does allow you to handle those. You can define the behavior. So that's the only reason I think they might have chosen label encoder.
Do you know how you specify that unknown? Because that's the issue number one that I ran into.
Scroll down, you should see. I saw it somewhere.
So I did it kind of like the long way, and
it may be it doesn't show it here, but it's maybe in the user guide.
It may just be a default behavior that they didn't bother to mention in the spec.
Could be.
Well, by default, if you give it a value that hasn't seen, you'll get an error though. That's the problem. Okay.
Yeah.
Okay, we can figure that out later. But let me show you how I did it. So
sure.
We have 5 features, categorical features: IP, app, device, OS, channel. For each one of them, we're going to do something. And for each one of them, we'll define a new label encoder. We're going to treat them separately. So for each column, starting with IP, we're going to create a new label encoder. We'll actually fit and transform at the same time that feature from the training data set. And we'll store that in this encoded one. And then we'll create a new column, a new feature called the original name plus underscore labels with this label encoded feature. And if you try to do this on another data set, like I was trying to do it here for the competition data set, you're going to get this value error that, Y contains unseen labels. And I'll show you how I run around this. But for now, I basically label encoded all these 5 features, and let's see how they look like now. So IP, app, device, OS, channel. Now we'll have IP labels, app labels, device labels, OS labels, and channel labels. I was looking at the data, and some of them look very similar to the original one, for example, device and app. So I was curious, okay, what difference did this label encoding make? So what I did is I iterated over these categorical features, and I'm summing up how many of them are actually different. What is the percentage of them that is different? Sorry. So I'm zooming a little bit, and I was trying to scroll here. Oh, there it is, divided by a shape. So IP, all of them are different after label encoding. App, only 3% of them are different. Device, 2%. OS, 9%. Channel, 100%. So for some reason, IP and channel, after this encoding, have completely different values, which I found very interesting. That goes back to maybe the information that you were saying, David. Maybe they have some additional information, and maybe after encoding them for the second time, like maybe some information is lost. I don't know. Okay. So now we have 1, 2, 3, 4, 5 extra features. At this point, we don't really need the original features like the IP, app, device, OS, and channel. We can simply create a model with these new features. There's a question on this exercise. We use label encoding here. Could you have used one-hot encoding? So basically create a column for each unique value of IP. So if IP has, let's say, 100 unique values, we'd have 100 unique columns. And to get an idea of maybe why that's not a good idea, we need to print out the unique values of each feature. So IP has about 260,000 out of 2 million records, 260K different values. App has about 300 different values. Device, about 2K, OS 200, channel 180. So these are high numbers to me. I don't know what's the maximum number that you use, David, but I think if anything is more than 10 for me, I wouldn't do one-hot encoding. What is your experience? I'm curious.
I've done, some that are, if it gets above 100, I mean, you're really gonna have a very sparse feature set and just very slow running model, usually, unless you have tons of compute resources, but I think that's generally the case.
Okay.
The other consideration here is what kind of model you're using. If you're using a GBM model like they are in this exercise, you can get away with not one-hot encoding your features because the model itself is able to put boundaries, decision boundaries arbitrarily anywhere in that feature.
Yep.
Awesome. Yeah, so here they're saying, you know, you have so many values, doesn't make sense to do one-hot encoding. Not sure where they got this specific value. When I ran the cell, like for IP, I got, you know, 260K instead of 58,000. Could be a typo. Cool. So we have our data set. We have created some extra features. Now let's actually split them into training, validations, and test sets, and let's build our model for our baseline case. Sorry, there was a question here. This is a time series data. So any special consideration we should take when we do this? How should we do the splitting? Can it be random? Should it be ordered? And if you remember, for time series data, it usually makes sense to order them by time and keep, you know, the majority of them for training, then the next batch or the next portion for validation, and the very last one for testing. Yeah, you don't want to mix up basically records in time. Okay, so we're going to keep 80% of the rows for training set, 10% for validation, and 10% for test. So again, this is the original data set. And let's see how we do that. We're only going to keep the day, hour, minute, second, IP labels, and all the different labels. So basically, we're going to ignore the original features that we had in the beginning, including the click time and the attributed time, as well as these attributed, because those are highly correlated, right? This is our target feature, is attributed. So the new features that we created, those will be the features that we'll be using in our model. So we store them as a list. So I forget, Kaggle has this feature when you click on it, tells you where your variable is being used. So these are our feature columns. We have this variable here, 10%, that we'll be using. First of all, since this is a time series, we'll be sorting our original, the entire data set by time, by click time. We will keep 10% for as a reference, and then what we'll be doing is we'll be keeping everything in our sorted data set up to the last 20% of the data. That's what this means, up to the last 20%. Then from the last 20% to the last 10%, we'll be storing that in this validation variable or data set. And the last 10% will be storing that in tests. So if you look at the shapes, from 2 million records, 1.8 million or 80% is training, 200K is in validation, 200K is in test. Cool. So we did our split. Now let's create our model, our baseline model. It'll be another variation of a tree-based model. This is a light GBM. So light GBM is a tree-based model introduced by Microsoft, I think it was in 2016, that I think works really great with larger data set from what I've seen online. And usually, I mean, it's not a rule, but usually I've seen online that it performs a little bit better than XGBoost. I'm not sure if that's your experience as well. So we'll import this module lightGBM as lightGBM LGB, and that one, if you remember from TensorFlow as well, it reminds me of that, has its own data set methods and data set module. So in this case, we'll be creating a lightGBM data set using the train data set that we created above with only the feature columns, and our labels will be the train is attributed. Similarly, for the validation set, we'll be storing that into this dvalid object, as well as for the test set. there are some parameters that this tree-based model uses. Number of leaves, objective binary, we'll be doing binary classification here, so 0 or 1. Number of leaves, I don't know if this is like a maximum or a suggested value. I'm curious if anybody knows. I didn't explore this parameter in detail. And for the metric, we'll be using this area under the curve. And number of rounds, how many times basically want to train our model? This is 1,000 times. And we'll be giving the parameters as input, the training set, how many rounds, the validation set, and we can also specify early stopping. So if basically our metric here, AUC, is not improving for 10 rounds, then we should stop. And when you execute this, if you don't specify the verbosity of it, it will just give you all the numbers. So it starts pretty well, 94% or 0.94 AUC and 0.95. Let's actually look at the graph. 0.96. Yeah, I think the only thing I changed here, I think I changed. Sorry, I wanted to capture the validation metrics. I think that's the only thing that I changed. So I found a post here on capturing the metrics so that I can later on inspect them and plot them. Yep, that was the only thing that I did. Yep. So this package actually has a plot metric method out of the box. And if you provide that validation metrics that you give as input and the metric you want to track, you can look here at the iterations in this area under the curve. And you can see that we're growing relatively well. And we're kind of plateauing here around 90.995, 96.2. I wanted to look at a little bit deeper into what features was this model using. So I'm using this plot importance method, and that will give you the features, the 15 most important features by how important it was for our score. So it looks like app labels was the most important one, then channel labels, OS labels, IP labels, and then the hour, minute, second. Device labels is the last one with day as well. So I find it very interesting. I want to look at some sample trees. So I'm plotting here like a very one of the many trees. It's kind of hard to see. I cannot zoom in anymore. But you can see I can tell you it's making decisions based on OS labels in the beginning, then OS labels, then channel labels and app labels. Again, this is one of many trees. So I think I printed out here how many trees are there. Let's see. No, I think there's like several hundred trees that were created. So we have a model. We know how it's doing on the validation set. What about the test set? So we have our test set here. We have our feature columns. We call this model that we have predict method on it. We get this yPredict output. Then we can use under scalar and has this metrics feature or this metrics library that you can use different metrics. We're going to use this receiver operator operating characteristic or area under the curve and get a score out of it of 0.97. So the higher this is closer to 1, the better it is. And our goal will be to improve this as we go on. So this is our baseline score using this baseline model with some very minimalistic feature engineering, I would say. Cool. So this was the first out of 4 sessions. Any feedback or questions before I go to the second one? Let me know. I haven't seen anything in chat, so let me know, Robert.
We're all good.
Awesome. Cool. Then for the second one, we'll actually look at encoding a little bit closer. And again, I'm looking at the exercise part of the Kaggle Mini course. So we'll be looking at different encodings. We saw label encoding in the previous session. Now we'll look at some different ones and we'll see how they improve, what is different about them, and how they improve our score. So we'll be looking at count encoding, target encoding, and cat boost encoding, and see how they perform. So nothing new here. Pandas, NP, pre-processing for our encoders, metrics to measure our performance, and LightGBM will be using again a similar method here. And this exercise, we don't want to go through all the feature or the minimal feature engineering again, and those steps are omitted by basically reading this new file again, which is basically the output of the previous exercise. It's stored in this Parquet file, baseline data. So we look at it, it has IP, app, device, OS, channel is attributed day, hour, minute, second. So it looks like it contains this day, hour, minute, second that we don't have to extract again. Then we define some methods of splitting the data based on a fraction here. Again, this is time-based, so we need to sort the values and then keep based on the fraction. Let's say 80%, 10% for validation, 10% for test, and then we return this train valid test. That's one method we'll be using a lot. And then we group into one other method called train model, different things that we need to do again and again, because we'll be creating multiple models. So if we don't specify feature columns, we'll be dropping click time, attributed time, and is attributed. Those are is attributed is our target field. We'll be creating our data set and storing them in a format that's appropriate for LightGBM model. Number of leaves 64. This is binary classification. Metric is AUC, and a seed just for reproducibility, I think. Number of rounds 1,000 again. Early stopping 20. Then we'll be doing prediction on the validation set. We'll be plotting that as well. And then if we have a test set, we'll be doing a prediction of the test set. Otherwise, we're just returning the model and the validation score. So now we don't have to call this large chunk of code again and again. We can just split the data, which is the original data set, in train valid test. And if we give it train valid, we're just going to get the model back and the score. So this is our baseline model, and this is how I'm keeping track of them internally. Cool. So for count, target, and cat boost, as we will see, many of them are based on some kind of a function that is looking at the entire data set, like counts or means or averages or order. So there's a question here that should you do this using your entire data set, or should you do this using just your training set? And if you remember from our data leakage module a while ago, we said that you should only use you should only compute any statistics just from the training set. You shouldn't expose your model to any test set. Yeah, so if you include data from the validation and test set, you'll overestimate your model's performance. It might do really well during training, but then when you expose it, the real world out there, you probably won't do that well. Cool. So count encoding, what is it and what does it do? So it counts how many times a value appears. So let's say we have countries in a feature. Let's say US, UK, Albania, Greece, Italy. And depending on how many times, say, US appears, we'll be assigning that value as the encoding. So the goal is, in our data set, if we have an IP that appears multiple times, we'll be assigning that a higher value. Let's say an IP appears 100 times, we'll be assigning that the value 100. If an IP appears only once, we'll be assigning that the encoding 1. So we'll look at categorical features again: IP, app, device, OS, and channel. We'll be looking at the count of each value in this data set. And we'll be encoding them using this count encoding.
George, can you make the font just a little bit bigger?
Yes, sorry, it was freezing on me.
Okay.
There you go.
Thanks.
That's the max. So from category encoders, we'll be importing or we'll be importing category encoders, and that one has different encoding mechanisms under it. And let's see how do we use them. So the first one I'll be using is this count encoder. The columns I'll be using them are these categorical features, these 5 features. And really, if you remember at the beginning, when I did the encoding, I did them in a for loop, and I had to create a new encoder, and I had to feed the data, and I had to append the new encoded data in the original data set. Like, there was a lot of work there. Look how nice and neat this looks now. You just provide the features that you want to encode, the encoder you want to encode, the count encoder in this case. You provide the entire set, which is the training set. Remember, we don't want to have any data leakage. The list of 5 features, and we just do a fit on them. And this internally will figure it out for each feature, for each column separately, how to do this count encoder. Then the other thing we'll do is, so that's the fitting part. Now, how do we actually apply it in our data set? So for the training part, we'll use the transform method here. This will return the transformed features. We'll join that with the original data set after we add this underscore count suffix. So we're doing 3 things at a time here. We're transforming the original features, we're count encoding them. We're adding a suffix underscore count. We're also joining them with the original data set. And that will be our train encoded part. We do the same for validation. And let's see how our data looks like now. So train encoded now should have, for the 5 features that we saw, we should have 5 extra features with an underscore count. So 68, this means that this IP appeared 68 times, the second one 4 times, the third one 118 times, and so forth. And for app, this means that, how many times that app identifier appeared. Cool. Let's train our model and see how we do now. So validation score, we get about 0.95. And I think that's more or less similar to the baseline model that we saw above. Let's see.
It's different.
No, it's different. Okay. So I had 0.95. Let me see what I had here. 0.96, a little bit less.
So we got worse.
We got worse. Yeah, a little bit worse. So there's a question here. Why do you think count encoding is a good idea, or why do you think it will improve the model score? So the solution they give you here is that rare values like will have a smaller value like 1 and 2 versus large values or common values will have a larger value. But again, I don't know if, unless you're more or less scale sensitive, like I don't know how that'd be a huge difference when you do your modeling, right? So I don't know if you treat number 1, number 2 differently than, let's say, number 1,000 or 2,000.
Yeah, I found this solution to be a little bit confusing, especially the part about classifying rare values together at prediction time. I'm not really sure what they mean by that or why you would want to do it.
Yeah. I mean, you're not grouping them, right? You're not grouping like the lower values together, and each one of them is different to me. Yeah, I was
a question in the chat as well. What about duplicates?
Duplicates.
I guess maybe that means if the whole row is duplicated.
So yeah, I imagine that you take care of that before you even begin this journey. You make sure you don't have any duplicate rows where basically every field is exactly the same. Then
I think he's asking, so let's say we had Great Britain they were showing, right? And Great Britain had 10 entries in our training. So you would give it a 10, right?
Mm-hmm.
But what if you also had, for Sweden, you had 10 entries, you would also give that a 10.
Oh, I see.
I think that's, maybe Eric can.
Probably not. Yeah, probably not. Probably I'll give Sweden 11.
Yeah, I mean, it's sort of like binning into buckets, right? So two countries might, or when you do like hashing tricks and stuff, things might hash to the same value. So this is the same concept, right?
Mhm.
You might get the same count for multiple categories.
Mm.
And the idea is that if this actually works, it's just saying that they contribute the same to the prediction, right? There's no difference between Great Britain and Sweden. Apologies to everybody who lives in those countries.
Yeah, but I'm hoping that count encoding in the back end is not binning them, but it's probably assigning them a different value. I don't know. I need to look at the code.
No, it just counts them and gives the value of the count.
Okay, then we're in trouble.
Yeah.
Then maybe this comment makes sense here. David and Robert, where do you go? On classifying rare values together. If we're actually doing binning, then, but that's not for rare values. That's for values that appear at the same time, the same amount of times. Okay, so that was one new encoding scheme that we saw. Let's look at another one. So this is target encoding. And the way that this works is you look at the target for one of the features. So let's say we have a country value, let's say Canada. We look at the is attributed feature, and for all the records where the country is Canada, we take an average of the attributed field. So let's say the average is 0.28. That will be the new encoded value for Canada. So basically, we are replacing a value with the average target value. So let's say US appeared 100 times out of 200, then that's 50%. So then the target encoding for US would be 0.5. If somebody appeared 1 out of 100, it would be 0.01.
Right. So, can you say it again, George?
So if somebody, let's say we have 100 rows, and we have a feature, let's say, I don't know, US appears only 1 out of 100 times.
Okay.
Then that value for US, the new value would be 0.01.
No, I don't think that's how target encoding works. I think that's more like so it's the average of the target for the US. So if you're looking at all the places US, I believe it's the average of the target that you put into the field.
Yeah, the average of the target. So, okay.
So
the target is 0 or 1. I'm saying the target is 0 or 1.
Oh, I see.
Yeah.
Well, but what's the value for the US? That's what's important, right?
Let's say the target for all of them is 1.
Okay, then you would put 1 in.
Yeah.
That would be the average for the US,
Yeah,
right?
1 out of 100. Yeah, just to make the math simpler. Yeah.
Okay. Yes.
Yeah.
Okay.
Yeah. If I had 2 records for US and one of them was 0, one of them was 1, the average would be 0. 1 out of, again, would be 1 out of 100. Right.
Say it again.
Let's say I had 100 records, but then I had 2 records for the US.
Okay.
With 0 and 1. It would just be 1 over 100 again.
No, it would be 0.5. It's the average of the targets that are labeled US, right? So
the average, right? So it'd be 0 plus 1 over how many records you have overall, right?
0 plus 1 divided by how many records you have for that target, or for
that target.
Yeah.
Okay. Then
it's like a group by mean.
Right.
so when you're doing the average, are you doing it just for the data set of this value, or are you doing it for the overall data set? So are you doing like 0 plus 1 over 1, or
it's the average value of the target for that value of the feature. Right? I will point out there are many different kinds of target encoding, but this is the one they're using the I think this one's called mean target.
So this would be 0 plus 1 over 2 then, not over 100. So 1/2.
Yeah. Yeah.
So we have a lot of records then that are in this in this group where half the values are one target and the other half are the other one. All of them will have the same value, 0.5.
You could end up with encodings that are the same for different for different values of the feature.
Okay, that's interesting to think about.
And the idea again is that they're contributing the same to the prediction, right? So.
Okay, so let's see, how do we use this? Again, very similar to the count encoder. It's just another library, another package called target encoder. We supply the categorical features and we fit it. Then we do the transformation. Again, we do this 3 steps at one. We do the transformation here. We add a suffix of _target and we join it with the original data set. And if we look at the head now, we should have, for the categorical feature, we should have _target. So IP target, app target, device target, OS target, channel target. And you see now they should all be less or equal to 1, between 0 and 1. Cool, let's see how this new encoding helps our models. So we look at our validation score and 0.95, a little bit less again than the baseline. And I think, yeah, this is where I'm grouping them. So I was trying to keep track. So 0.96 was the baseline one, 0.95, 0.954. So very similar to count encoding, a little bit less than baseline. Another exercise that we did here was we were ignoring the IP. For some reason, we thought maybe the IP has some kind of a lot of noise to it. Basically, we don't want our model to find specific IPs and somehow pay a lot of attention to those IPs. Like, so we basically excluded IPs from using them as feature as well. So we did the same. You will see now there's no IP. There's no IP target. Then we use this only on the encoded part and the validation encoded part. And let's see what we get. We get a little bit better score, 0.9627, which is a little bit better than the baseline one, 0.9622. So we're able to learn a little bit more there, excluding the IP target. Yep, that's what we did. So then why was this helpful? So I think that the message that I took away was that if you have new IPs here that were not in the training data set, you don't want your model to give a lot of weight, a lot of attention to IPs. So because IPs usually are unique, right, depending on where you're coming from in the world. So you don't want your model to pay heavily, to keep that as an important feature in your model. Do you have any better explanation, David or Robert? I mean, that's the one that kind of felt okay to me.
Yeah, it almost, it basically said, the IP is kind of noise, and we were overfitting before, right?
Mm-hmm.
Yeah, I mean, if it's almost unique for every record, it's kind of analogous to using a social security number to predict a likelihood of default or something.
Yeah.
There are quite a lot of ISPs and our providers who you're getting dynamic IPs. So if you're trying to get something out of records across time based on IPs, they're changing all the time anyway. So it's kind of like, it's purely random.
So yeah, the same user probably will show up with different IPs based on
Absolutely.
different days. Okay. The last encoding we'll be looking at is this cat boost encoding. So I think the only difference between this and the target encoding is that you don't look at all the records, or you don't look at the average target value for all the records. You only look at the average for all the records before you. So it's almost like a sorted version of the target encoding. I don't have the good explanation that that they had in the course, but to me this is just a modified version of target encoding. Is that your understanding as well, David, Robert?
Yes.
Okay. So then, in a similar way, we used it in the previous methods as well, or the previous encoding mechanisms. Yep, I removed IP as well for here, since we saw it gave us a little bit better performance, so I excluded IP. Then we looked at this cat boost encoder, the categorical features excluding the IP, random state. We fit it on each feature separately. We transform it. We add a suffix here, cat boost CB. We join it with the original one. We store it in this train encoded data set. Same for validation. So now we have this underscore CB. Then we train it, we get 0.9628, which is a little bit better than the best one we had before, the target one with no IP. So this is cat boost with no IP, 0.9628. Cool. Yeah, that's the same numbers. That's what I had for different encodings. If there are no questions, I'll turn it over to David to continue with more feature engineering.
Question, did anybody try to use all those together?
Aha. I think in the next one or the last one, we use way more. Yeah, you're right. Right now we used one at a time, but later on we're going to use multiple at a time. But I don't know if we used all this specifically or other ones. Yep, good question.
So I was going to show, before I go into my sections, I did a little bit deeper dive on this. Let me try to find where it is. Never find.
Let me enable. There you go.
Okay. So I was curious, you know, I changed the training function just to print out the columns that are being used, and just to verify. So like this is the cat boost one, right? And here it's got the original IP app device and all that, and then they're tagged on the cat boost feature. So that's normal. They would add them on to there. And I just for curious sake, just for out of curiosity, I thought, well, I want to drop the original categories that they actually did and just see if we just keep these cat boosts in there, does it do any better? And I did this for all the different approaches, the target encoding, the count encoding. And you can see here with the additional features, we got 96.28. When I dropped the original ones and kept the app cat boost and all those, I got 96.22. So it actually went down. So it's good to keep the originals and the new ones that are add-on. And that, you know, that's showing my probably my neural network background, where we normally might replace them instead of adding new ones. But anyway, I just thought I'd show that it's important to have all of them and add more and more.
What did you say about neural networks? You'd replace, you'd add, or you'd replace?
Well, normally neural networks, I'm letting it learn what features are important, what aren't, and hopefully it constructs all these relationships between features, you know, and you don't have to do all this. But if I was to do some encoding of a feature, I would typically replace that feature with the encoded feature. I wouldn't keep the original as well. but obviously these are tree-based models, and they work much better this way.
Okay. Cool.
Yeah. Okay. Hopefully everybody can see my screen okay.
Yes.
So the next section is on feature generation, and I'll go into that. Let's see it over here. The first idea here is where they're creating new features out of the features that we already have. So we're going to somehow do different things to our current feature set to produce new features. And one of the most straightforward ways is to do what is known as interactions, where you basically combine the features together. Typically, you do this for 2 of your features at a time, but you can do as many as you have. Here's an example where they're talking about a Spotify. I think it's a Spotify database, and they're saying, you've got a country feature as well as a category feature for the different kind of thing that they're. I'm not sure it's a Spotify. I forgot what this is exactly, but but they're going to combine them. So if you had in a row you had Canada and music, you would produce a new feature called CA_music, and this is known as an interaction. So they're going to do what we had before, do label encoding on our categories, and then we're going to do some things to put them together. We're also going to do different counts in terms of what's going on in terms of, and I think this is the Kickstarter database.
Yeah.
Sorry if I thought it was Spotify. This is the Kickstarter one. So this one, we're going to look at some statistics around the activity during the week, and capture that into a new column. And they go through how they're going to calculate it. They're going to do this rolling calculation to get it, and then they're going to talk detail about how they track the index on this, so you're looking back at rows prior to you and calculating this as you go, almost like a volume, running volume or a running tally that you're adding up as a new feature. And here's an example of it over time, how it varies. And it's a rolling tally over the 7 days. So we're going to add that as a new feature. We're also going to look at the time since the last project happened in the same category. So we're going to basically go through and group based on our categories and look at the time from the last one that was launched prior to the current one. And we're going to put that as a new feature on the current row. So that's a different way of doing this. Sometimes if it's the first project in that category, there won't be a value for time since the last project because you're the first one. So in that case, they'll put a empty value, not a number in there.
So a little bit about the logic why we added those specific features, David. So the first one was
so the first one was just the interactions.
Mm-hmm.
And a lot of times when people are trying to assess, they'll do an interaction for every feature between the multiple combinations, all the possible combinations, because you don't know unless sometimes you have insight, but if you want to test it, you might do for all of them. The number of projects, I think here they have to know something about the data set and the fact that, maybe where this is important, right? So if there's been a lot of the same project kicked off in the last week, it's going to make a difference on our prediction.
Yep. Yeah. You basically, that's your competition, right? If you have a Kickstarter campaign.
It's possible if you're not unique, you're going to be less likely to succeed in Kickstarter. Mm-hmm. Again, this rolling is sort of like the same thing in a different way of looking at it. It's more like just a recent time snap of that same idea that, well, maybe if it's been, a year since someone did this, maybe it doesn't matter that last year they tried it 20 times, but if it's been a whole year since they tried it, maybe I have a better shot. So I you know, there's some logic there. Okay, so we went through that. And those are mainly dealing with categorical variables. Here we can do, we can also do this with numeric features. So we haven't talked much about any types of feature engineering around numeric features, but this is one of the first ones we're going to address that. Here they have a goal where the project is, you know, how much they're trying to raise for their Kickstarter. And we're going to, we talked a little bit earlier, I mentioned bending. And so here they're going to bend the goal into 50 different bins. So they're going to basically group this into 50 different bins. And there's lots of ways to approach binning. Oh, sorry. They're doing the most straightforward method here. So we're going to plot this first and take a look at this. We can see that it's highly non-uniform across the bins, right? So across the distribution here of our range of data, most of it's going to be very small. Most models do better with uniform distributions of this, normalized distributions, and we're not going to have that feature with our tree-based models, but they're showing, I think, how we could further adjust our feature here by kind of scaling it. And they talk about we could take the square root. That helps a little bit to more even out our distribution, but we do better if we do a log transformation on it, and we get a nice looking distribution there that's centered and pretty even on both sides. So this is going to help with some models. As I mentioned here, tree-based models are invariant to this scale, so it doesn't matter. But if we were doing like a linear model or a neural network that a lot of us are very familiar with, this will be an important thing to consider. And then let's go to the exercise and see what happens there. So here we're going to look again at the same competition of data set for the app clicking and downloading. They're going to go ahead and label the category features with the label encoder, and then we're going to build. We have the same training thing we had before approach. I printed out the features just to show what it's actually using behind the scenes. So here's our baseline model, same as before, 96227, with just the basic features. And the first thing we're going to do is try some interactions. So we're going to look at these categorical features. We're only doing this with our categorical features, and we're going to build combinations of 2. And we've got a tool here that helps us go through all that list and build combinations of 2. And we're going to give a new column names, always underscore. So we see things like IP underscore app, IP underscore device. And we're going to get the values here by just putting together the values of the categories, the strings, right? So we're gonna go ahead and fit that also with our label encoding. So we've also label encoded that, and we'll train with that. And here I printed out these. You can see now all the combinations in there: IP OS, IP channel, OS underscore channel. And it did actually improve our model some. So we got, instead of 9622, I think now it goes to 9626. So we actually got an improvement by taking into account in this interaction. Generating, we're going to look at some of these numeric things, the same kind of thing we looked at before, where we're looking back, how big was the volume of events in the past 6 hours? So we're going to do something there where we're going to go through and do this rolling calculation over the last 6 hours and see if that improves our result. So here we do the calculation, and you can see the last new column we've added is IP pass 6-hour counts. And we've kept the prior interaction features that we added. So here we're doing multiple features generations. And this leads to 9647, which is our best result so far. I think we were seeing 962 something, 7 or 8 or 9 or something. So we're still improving. They talk about that, again, this is sort of like we talked about data leakage before, but we don't want to do features from the future. So we're not going to look at volume going forward or anything where we're using feature information that we is beyond our current row when we're talking about, especially something like this that's time sensitive, a time series. How about we do something like, this is again sort of like what we did with the prior data set in the tutorial. We're going to look at time since the last event. So we're looking not only up here at how much volume we had or how many events, but now we're going to look at the time since the last event. So, and here we do like a time difference calculation. I'll let you go through that. It's not too complicated. And when we run that, we get 9651. And you can see here's our past events that we've added in here. So they did this over a couple of ways of doing it. What was the value? 9651, and we had gotten a 9647. So again, we've improved. So we're continuing to get better results. We're adding quite a lot of new features. Now, one thing we want to look at is maybe the number of previous app downloads, since this is what we're trying to predict. This is the idea that a user is more likely to download again if they've done it before. So that's going to add this new, where is it? Somewhere.
I think there's a typo here. I think they stored it in under IP past 6-hour counts, which is used somewhere before.
Oh yeah, so they actually put it in this. They overwrote the.
Yeah.
So mistake on their part. We should try this again and see if we can improve it.
Mm-hmm.
Yeah, 9652, not much of an improvement, but maybe they would have gotten better if they hadn't overwritten their other feature. So they asked the question, would these features generated work well for neural networks as well as the tree-based models? And it's kind of a strange answer they give. They will work well for either one. Most likely they'll improve both. The only thing they do is put a caveat in here that our tree-based models our neural networks need our data, our input data, to be normalized basically, or scaled all to kind of similar scales so that we get better results. And so they talk about that you could do this with the standard scaler. And we've discussed this in other topics that we've gone through, how we can do those kind of things. Any questions about this type of feature generation? This is just a small subset. You can do a lot of different things. I've seen people take, a numeric feature column, and they'll do things like try squaring it, different ways of producing new features based on it. You may have things where you look at differences between features, numerical features. If you're doing something that has latitude, longitudes in there, you might do, calculating distances. There's all kinds of many different types of feature generation you do.
Mm-hmm. But in every case, you add to it, right? You add to your original list.
You're adding to your original, yeah.
I might have skipped this, but you had a column called past events or past 6 hours. I don't know what was the difference between them. The one before this.
Yeah, it's right up here. So I think it's up here.
Yeah.
Yeah. So they're gonna generate past events and then past 6 hours events, right? The past event.
So that's past events 6 hours. I understand that. Then what is past events? I forgot.
Yeah, why did they get past events in there?
I think maybe they had it like that in that Parquet file and that you imported. So they basically
They may have already had it. Yeah, did they?
it took a while to calculate. So here's the Parquet file. We calculated it for you, and maybe they named it past events.
I don't know. I don't see it. I'm not sure where it's coming
So
actually.
it's from that past 6 hour events.parquet.
Oh, they've got a they've got a they brought in a new one.
But then you create a new one called past event 6 hours, not here.
6 hours, yeah.
Yeah, it was.
But they set it to the same thing and then they don't remove it. So I don't. That's kind of like having the same feature in there twice, right?
Yeah.
Well, it's a mistake on their part. I think it's probably a typo.
Yeah.
I printed this out, so this is a nice thing to maybe, always check things like this. Right? When you do feature generation, make sure you've actually got what you think you have in your data. So maybe that's a good something to learn, right?
It's worth noting that this kind of feature duplication is fine for tree-based models, but can hurt you depending on other choices of model.
Right. All right. So I'll move on to the next thing. We're going to talk about, to Svetlana's point, you're adding all these things together and you're generating, literally you could generate thousands of different features based on your data set, depending on what you have. How do you know whether they're all worth keeping around? Because you're at some point, you're really starting to make it easy for your model to overfit if you're generating a lot of noise in your training. And you're also, it's becoming computationally expensive to do the work. So for your model. And especially when you get to doing actual inference in your, whatever your end deployment is, you don't want to be having to pull more features than you need in there, right? You want to have the minimum set that gets you the prediction accuracy you need. That'll help you with speed, also with the fact that whatever your interface is, where the data comes in, you don't have to generate thousands of features coming in, right? So let's talk about how you might handle that. So this is where feature selection comes into play. And there's many different ways to do feature selection. We're going to introduce a couple here. The first one is called Univariate feature selection. And they're going to use a module in sklearn, which is really useful for this, called select k best. K is the number of features you want to limit your model to be using. And all of the select k best methods take in a scoring function, which is a way of testing the accuracy of your model as it goes through trying out the different features. And there's a lot of different scoring functions. They're all kind of have tests, these chi-squared, these f-value ones. There's this thing called mutual information. So there's a lot of details on this that are covered really well in sklearn manuals, but I'll talk a little bit about a few of them that we're going to use here in a minute. Does that make sense, kind of how we're going to be selecting the best features, that we're going to score different combinations of them and then choose the top 5 or top 10 or whatever we think we want? Okay, so let's see how it happens in practice. So we're going to, in this example, they're going to select the top 5 and they're going to use what's called F-classif scoring. It's there's a different one for regression. So you would see there's this SF regress or something like that. It's so it's important to pick the right one. These are appropriate for classification problems. And then we're going to use this selector to fit and transform, just like most of the transformers, same kind of concept that you have in all of the encoders. So it's the same, this transformer approach. of sklearn. We're going to put in all the feature columns, the data, and then our Ys, or our target data. And that's going to produce out a new set of features for us, all the rows, with only 5 features total. Now, they wanted to show something that, you see a lot of people do wrong with different encoders, which is that we actually did this on the full data set. And we don't want to do that because we're fitting on our test data as well, right? And we only want to do that on the training data. Otherwise, we're introducing data leakage. And so that's the point they make. So they go back and they do it again just on the training features. So they split the data set out and do this just for, and here you can see you're going to get different values, right? So very, very different values in here. If you look through it, you'll see there's some. The other thing now is, of course, we're going to need to apply this to the, we're going to need to apply the transform with this to the validation set eventually down here. So, but it'd be interesting to know these are 5 columns that represent these new features, and the most important features. They're not new, but they're just the most important features. But we don't know what they are. They're just numbers, right? So it'd be nice to know what they are. So here you can get back and see this is the way to get back which ones they were. And what this does is it zeroes out the ones that are no longer going to be used. So for instance, categories being thrown out, goals being thrown out, hours being thrown out. Year is important, so it's being kept. Currency is important, country is important. But some of these interactions like category, currency, category, they're being thrown out as well. We're keeping a few of the interactions though, so we benefit from some of them. So we've kept most important ones. We're going to use those here and prune out the ones that had 0 variance. So basically they're all the same value. They're all 0. So we're going to remove those and keep the ones that don't have that. And in the exercise, we'll go through and see how that helps us or doesn't help us.
So you called the fit transform there, but you didn't actually train any model, right? You're trying to see how your target value is, or target feature is correlated with these 5.
Yeah, that's essentially what we're doing. We are actually going through and doing a type of scoring of the target. Yeah, how it was correlated. And there's several different ones that, like I said, there's a lot of different scoring mechanisms you can use. You can also introduce your own, but these are some of the most popular, the chi-squared, the ANOVA. This is this F1, which we used. We used this F classifier. This is this ANOVA technique for doing it. And there's another one called mutual information scoring.
So the one we use measures linear dependency between feature variables and the target. So it's trying basically to figure out if there's a linear combination of these 5 columns.
Yep.
That best predicts the target.
Yep. So if you've got features that have a nonlinear relationship, this F value is not going to be the proper one to use. It turns out the mutual information score does do capture some of the nonlinear relationships between the features. So, so that's one approach. Another approach is to do L1 regularization. And if you're familiar with like lasso and logistic regression, things like that, you're basically going to use this thing called select from model. And what we're going to do is, L1, and they're going to punish they're going to basically set the weights on, which are what they call coefficients here, right? In like a linear or logistic. They're going to set to 0 the coefficients for the features that are not important. So that's another way to do this. You're going to run the models and get those coefficients out, and then use that to select your features, which then once you have those features, you might run it with a more sophisticated model, right? So tree-based or a neural network or whatever. So to do that, we're just gonna go ahead and again, run it here against an X and Y, and our X and Y is our training features, and the Y, of course, is our target again. So, but we're actually gonna run the select from model, which is gonna run the model against it and give us a result. Once we've got that kind of L1 regularized model, which has these coefficients that are zeroed out, we're gonna transform our feature set with that and get our new feature set. And again, here's what you get. We need to then go and do the same process we did before to actually get the column names and see what features we've selected. We're going to look again for ones that basically aren't set to 0.
So again, there was no model train here, right? So you
Well,
were looking for a linear combination of columns, or
you're applying lasso or logistic regression here, right, as the model that you're going to do this with. So you're using like a simpler model to make your selections. I will point out there's other ways to do this, but these are the two approaches that they're showing here.
Mhm.
Okay, there are more sophisticated ways to do feature selection. So let's look at the exercise and see if maybe it'll help answer some of our questions. So again, we're going to look at that download ad fraud application. In this case, they're going to have a lot of different Parquet files that they're bringing in. But the idea is that that's going to enable us to produce lots of different features. We're going to combine them all together and generate with our feature engineering. We're going to generate a whole bunch of different features. And I think if I remember right, it's like 90 features we're going to have to start. So we'll go through same kind of modeling. Again, I printed out what features they use when they get to actually run this. So our baseline here, I printed out the 90 features that come with it, and our baseline score is 0.9658. So remember that. So which ones are going to use for feature selection? Well, we know, we talked about this before, that we should use the training data, right? So we don't want to include our validation or our test data because that would introduce leakage, especially when we're talking about a time series. So actually I was wrong, there's 91 features. So I knew it was something like 90. So let's apply that first technique they showed us with called Univariate. We're going to do select k-best and use this. We're talking about a classification problem, even though it's a binary classification problem, it's not regression. So this would be appropriate ANOVA scoring to use. And just like in the example, they do what they showed before, where you do select k-best, you give it the scoring function, and then how many of those features do you want to keep? And here we are going to go from 91 down to 40. So we go through and we fit the training only, right? And the target Y, and we're going to get back our new feature set. So we're going to go through that process of building it out so we can see the names. Part of the reason we want to get that is we're going to find out which ones were dropped, and they're going to test that, right? So we want to capture those drop columns because they're going to apply that back to the different data sets, not just the training data set, right? So we got back, if you want to think of this as the training data set with the new features, okay, but we don't have validation or test with only the sorry, I shouldn't say new feature, I say only the reduced feature set, right, that we've selected. So we want to capture which columns were dropped. so that we can also drop them out of the validation and the test data. Does that make sense? Okay, so here we're going to do that. We're going to train our model. You can see this is not the original 91. This is our 40. And we get 9625. Let's go back and see what we had before. We were at 9658, so we actually did a little bit worse. So in this case, reducing it from 91 to 40 hurt us. But depending on your application, it could be that that very, very small difference in accuracy doesn't matter for your application. So maybe this is a plus for you. You were able to eliminate more than half the data, more than half the features, and that could be significant for your actual throughput and things like that. So how do we choose? They chose 40, but how do we choose what the best value of K is? You can do this over and over again. As long as you're getting, your threshold of accuracy or whatever criteria you're going to do. This is kind of like a hyper parameter optimization exercise in a way. All right, well, what about the other way they told us to do feature selection, which was L1 regularization? We're going to write a little routine, a little function to do this for us. We're going to use logistic regression, and with L1 is the penalty that's going to use in there. And we're going to do that as before. We showed we'd have the select from model with this logistic regression. Then we can transform our feature set and get a reduced feature set. Note that I haven't told it that I want 40 or how much to reduce it, right? So I have nowhere I've told that. But again, we're going to figure out which ones to keep, and I'm going to look at it. I'm going to run it and look at it. So here, I had to do some coding. I think they may have had some errors. I don't know if you guys, I couldn't get this to run the way they had it, so I had to do a little change. So basically, I'm going to run it up there with my train features and my label. And I'm going to print out which ones I'm keeping, but I'm going to go ahead and look at all my columns and remove the ones I'm keeping to produce a dropped set of columns. And then I'll apply that to the training, validation, and test set and model it. And when I looked at this, I counted them up, and I think there's about 60. So before, I think we reduced to 40, but here with L1 regularization, it kept about 60 of the features. And that gave us a result of 9659. Which, let's see how 60 does as opposed to the 40. So our original 9658, so we actually got a slightly better, just marginally better result. But it, was much better than when we only had the 40. So L1 regularization worked with that. So they make a point here that we're doing a tree-based model. We may get better results with using another tree-based model for feature selection instead of using either lasso or logistic regression. When we did that select from model, we could actually use some simpler, like maybe a random forest or something, to do that selection for us, and it would select features based on that.
So the way you do that is run random forest and pick the most important features?
Yeah, so back here where we did the select from model, we put in the model that we're using to do that with. In this case, it's logistic regression, but we could have done this with random forest classifier, or they mentioned another one, something like there's this thing called extra trees classifier. There's a lot of different types of tree-based models. But they're not as complex as the LG BM or like XG Boost or something. But so use a simpler model to help you select your features, and then you would use those features in your bigger, more complex model.
That's interesting. You're using a tree model to optimize your tree model.
Yeah, to optimize the input to your tree model, right?
Yeah.
Yeah. So. Yeah.
There was a comment about that value of C, yeah.
Yeah, so it's basically you're saying before we were using select K and we could choose K so we know which features we were going to get out. Here they're saying you have to change the C value that we put in to, but you don't know basically ahead of time. You have to, I think you have to actually, run it. There may be, I don't know, maybe there is a formula you could use. I don't know if anybody else is more familiar with this than me, but it's possible that there's a formula where if you know something about the size of your features and you know what value of C to use to get a certain amount. Any questions, anything in the chat about that?
I don't see any questions. Yeah, feel free to post them on the chat or unmute yourself. Nice. I like the session too.
Yeah, it's fascinating.
Thank you, David. That was very useful. I would love if we could spend a little bit of time and talk a little bit about the competition. I know you and I put some notebooks together. I can share my screen a little bit on what I did, and I'd love to hear from you as well.
Okay. Let me see if I can, maybe I'll check and see if it's running again. Maybe I can just show my recent.
Yeah, otherwise I have
yours first.
Okay. I'll just show the findings that I was able to work through, and I put them on Slack as well. So I'm just sharing the Slack one here. But basically, what I did is
it helps you, George. It seems like they've got their Kaggle engines running again. Everything's working.
Oh, really? Okay.
So
yeah,
that helps you.
That's okay. Can you see the Slack channel here? I don't know if I can zoom.
It's very small.
That's the thing. Okay, hold on. Let me paste in here. All right.
Yeah, that's better.
So the challenges with the competition itself is, first of all, as I mentioned, the memory size itself is, I think, about 7 gigabytes in size. There's 150 million records, as well as label encoding issues, meaning you want to make sure that when you do the encoding on the training set, you're probably going to see values in the test set or the competition set that you haven't seen before. So, how do you handle those unknowns? That's important. And then what I have here that I shared in Slack as well is I was using a very small subset of the training set. This is before I figured out a way on how to actually sample the competition data set better. And I took some notes from you, David. So before that, I was simply looking at maybe 1 million records out of 150 million records. And I was having about 1.5 million values that I didn't know how to label encode in the competition data set. I was getting about 85 score, 0.85 in the validation set. And when you upload your submission in the competition, I was getting about 0.83. Then I increased this is without any sampling, okay? And this is still using this imbalanced data set of 150 million, but I was just looking at the first 10 million records. That gave me about more or less the same result. 20 million records, didn't do much. Where I saw a huge jump was using this data set that was sampled properly. So instead of this 99% negative samples, this feature engineering data set had about 20% positive and 80% negative. So that is about a 2 million record data set, and that gave me, with just a baseline model, I was able to get actually the best score of 95.
How did you get the feature engineering data? Are you going to go through that?
Yeah, I'll go through that. That is just the label encoding of IP, app, OS, channel.
Got it. Okay, great.
Yep. So just that, I was able to get the best score. Then let's see what I changed here. Then count encoding actually gave me worse examples. Target encoding, even worse. Target encoding, no IP. I mean, a little bit better than this, but still not as good as the baseline. Cat boost, 79, 81. So, and then interactions, I did interactions as well, 82, 82, 80, yeah, 82. But I was surprised at the baseline one with just the label encoding for those 5 categorical features, gave me the best one. Later on, I used Dask later on, and I'd love for you, David, to go over your notebook of sampling it and doing a better job of pre-processing the data. Then later on today and yesterday, I was playing around with a deep learning model, and I'm still working on it. I'm not getting the best result out of them, so I'm still working on that. But that's
just for context, I think the winner of the competition was only like 90.98. So for such a straightforward approach, you're very close. I mean,
well, if you look at them, they're all yeah, they're all so close to each other. All
I'm sure they did much more advanced things, but that's a good result. 0.95.
I mean, all of them are like 0.98.
Yeah,
and it's 0.98 for the first few thousand records. So I don't know.
but you can see some of them. I mean, 238 submissions. So they were working a lot longer than you at this.
Yeah. But yeah,
Losing out that last 0.03% accuracy.
Yeah, and then my next thing would be to maybe look at some of the discussions, because I think some of them actually say what was their approach.
It's a great way to learn. Yeah, they often will go back through their notebooks.
Yeah. Yeah, I mean, I like the journey of just starting with just not even sampling the very first few records, then 10 million records, 20 million records, then using this more balanced data set and just the baseline one, I was able to get this 95, and then it didn't improve me with these encodings. I was surprised. Cool. Robert, I'm curious about your notebook, and David, I'm curious about your notebook and some of the new things you included that I had never seen before. You're muted.
Okay, can you see it now?
Yes.
Okay, so I went against the convention here of everything we just learned, and I just wrote a deep neural network to see how I could do on this. So George mentioned the fact that the huge size of the data set makes it impossible to bring it all into memory with like normal things we use like pandas. So I used Dask, which is really nice for handling very large amounts of data in Python. So I'm going to use specifically the Dask data frame, which operates pretty much exactly like a pandas data frame. It has a few functions that it doesn't support, but it's very close to a one-for-one functionality. And so I'm going to read the data frame. I'm going to define the types. This saves a little bit on memory usage if you can, instead of using some of the standard, float 64s and things like that. Since I'm going to consider these to be categories and not numbers to me, I went ahead and read them in as objects, as strings, just like they're any other kind of category. So the fact that they're numbers doesn't have any meaning to me other than it just tells me what category they are. So here's that Dask data frame where I'm doing a read. It's just like what we would normally use. Here's the I'm defining the types for the read-in. The other thing is there are more columns in the actual CSV than what I'm doing, but I'm only going to pull in the ones that I use. And so again, this also saves in memory. So you can do things like get the info about what kind of data frame you have without actually going and looking at the full data frame. So you're not really using much memory when you do some of these operations. There are operations I'll show you later that then pull in a lot of the things in the memory and you start using it up. But these some of these things do not. And you can look through DAS documentation to figure out. So here's what we have. Nothing new that you haven't seen before. But what I wanted to do is look at the ones that are, this is a binary classification. I wanted to look at ones that are true, or it is attributed, and ones that aren't. And I'm going to create a DF here, which is just it's another data frame basically of only the true ones. And when I call compute, that's actually going to pull all these values. Now this is the smaller set.
Mm-hmm.
This is a highly imbalanced, as George said. So this is a small number. It's not gonna kill us. And right here, I actually printed out how many. We only have 456,000 rows where this is true, and that's out of what 150 million.
Yep.
Total. So a small amount. So I'm not worried about memory there. When I do compute, though, it actually pulls them all over. And this actually changes. When I did this, it was just still a DAS data frame. But when I do compute, I now have a pandas data frame. So that's what happens with this operation. And the reason I did that is at this point, I'm safe memory-wise to do it. I'm also going to want to do my work with the data frame, a pandas data frame, as opposed to DAS. So I'm going to do the same thing here, where I'm going to only select the ones that are false. And this is the very, very large amount. But what I can do, I'm still working in DAS, so I haven't actually pulled anything into memory. What I can do is then sample that, and I'm going to choose a really small fraction of that, 149 million or whatever it is, right? And when I had to play with this to get the number right, but when I choose this fraction, you could probably calculate this. I just just did it by hand. But now I'm going to pull that into a pandas data frame as before. But you can see it's small. It's almost the same value. It's very, very similar. And I don't have to worry about memory because I didn't pull 150 or 149 million something rows into my environment. Just want to give a sample of this second one just to show that they're all 0. And now I'm going to produce a training set by concatenating those two together. And you can look at the value counts here and see that now I have a very balanced data set to train on.
Nice.
Here's my info. And then I go about with some of that feature engineering of creating our standard things we're used to. I'm going to take out this click time because it's no longer of value to me. I'm just going to keep the day, hour, minute, and second that I broke it into. So here's my values again. So next thing I'm going to do is break up my training data into a validation set. And one thing that's important here is that I'm going to be shuffling. And this is the default, but I just wanted to show it to make it clear that I'm shuffling these data. But I'm also stratifying on that target value so that I keep a balanced data set in both my training and my validation data sets. I'm keeping out about 20% for validation. I use a little helper function here to go from these data frames, pandas data frames, into TensorFlow data sets. This is probably seen this several times, but key things in here as I create my data sets. And if I want to, I can shuffle them just like I would batches coming from other places. I'm also going to batch them up and I don't remember, I think I chose 32 as the default coming in. If I have labels, I would keep them. In the case of like a test set, I'm not going to have labels, so I won't worry about that. What else? That's about it. So here I create, with that helper routine, I create my training and my validation data sets. I actually did a much bigger, it ran faster the bigger I could go, so I did a bigger batch size, and I have a lot of data here. The other thing I'm going to do is prefetch with this auto tune that George looked at before. This speeds up the feeding into your GPUs. And I'm going to use something we haven't gone through, which is a feature in TensorFlow called feature columns. And this does a lot of upfront work for us in terms of how you would pull in categorical columns or numerical columns or identity columns and things like that. And so there's a whole bunch of ways you can address them. So the numeric columns just come in straight forward. They're just, in this case, I used IP as a numeric column. Go ahead.
What is it doing if it's a numerical? Is it?
Just taking it as it is, basically. It's not doing anything special to it, right?
So it's just taking it from an object and making it a numeric type for the network.
So IP, I actually left as a numeric.
Oh, okay.
So I didn't have to do that. Yeah. I would probably have to do something special if it was, I would have to treat it as a category column and do something different, right? So here it's a numeric column already. So I just do that. For the category columns, now I'm gonna do some treatment for them. So what I did was embed them, treated them as just like you would, text or something. But you have this concept of an embedding column where you're going to replace the string with a vector, right? That's learned. So a vector of numbers, of a certain dimension that are then learned. It becomes part of your learning parameters. And you want to build that off of a vocabulary of all the possible values you have. So I'm doing that by just looking at the unique values to build up my vocabulary list. And I'm saying this is going to be a category column where I'm embedding it based on that vocabulary. I assume it, I should look into this, but I assume it also has an out of vocabulary.
I was going to ask.
As well, to handle for, you might encounter values of app you've never seen before. Maybe not, but. And then you can set the dimensions on it. It's sort of like very similar to an embedding that you would use for any kind of text. Right?
So we're going to have the NLP adventures with it.
Yes. So if you've done any, so we're going to add this to our list of feature columns. I'll do the same thing for the OS.
Now you're training that embedding simultaneous to the whole network, though, right?
That's right. Just like in NLP, I'm going to train the embedding that's used for these categories.
Yeah. Okay.
You don't want to go with count or target or cat boost encodings here.
So maybe some of these OSs, like, I don't know, maybe devices, if you look at that, maybe it's smart enough to learn there's some similarity between all the ones that are iPhone something, right? And maybe the Android ones get grouped, if you looked at the embeddings after training, maybe there's some relationship. Maybe not, but. So I do that. I'm going to do the same thing with day. Maybe you guys hadn't thought about this in the past. I know some of you have, but if you think about things like days, hours, minutes, seconds, they actually are categories, right? There's only going to be so many hours values, right? And they're categories. There's nothing to say necessarily that 2 o'clock is half as important as 4 o'clock. So you wouldn't want to assign them as necessarily as numbers. Maybe this is not important for like a tree-based model, but for like a neural network, it's important to think about maybe these things as the same thing I would say for if you're using dates. Dates are actually categorical.
Oh, really?
But for a neural network, might it be important for the network to learn similarities of adjacent hours, right? Maybe it should be predicting similar values for 2 and 3 o'clock and different values maybe for 7 and 8 o'clock.
That's right. And I'm hoping that by embedding it, it'll learn that,
Okay.
right? You're hoping that it'll learn those, what is the actual relationship between them. So,
It seems
go
like another, you could have just kept it as a numerical feature though. It'd be an interesting comparison.
Yeah.
right. Yeah, that would be something to try for sure. Once I have all these feature columns, which can be a whole bunch of different types of, you build a layer that you're going to use in Keras called the dense features. It's just a way of wrapping them all together. And I can put that feature layer into a model. So here I'm putting it into a sequential model with a few more dense layers, and it's binary. So I'm doing a sigmoid activation. Use Atom. I did a slightly smaller learning rate than the default because I thought it was stopping too fast and training not to the best. You probably would want to do some kind of more functional, function to replace the learning rate where you ramp up and ramp down and all those typical techniques that are used to get to the very best value that these other people in the competitors are getting to. But this is more like just a example of how to do this. Binary cross entropy, and I think the metric was some form of AUC was the metric they were using. So I'm just looking at that for my own telling. Going to do the typical thing of early stopping. I said run for 200 epochs and stop early. And when I end up running training, I get to 57 in this case. Epochs ran before it stopped. And you can see I was getting like my validation was about 96 something consistently, 96.4. So I plotted that out, and you can see this actually was a lot smoother when I used the standard learning rate. But when I use the smaller learning rate, it jumps around a little more. It becomes a little, it doesn't converge quite as fast, I guess is the way to put it. I just go through the same thing with getting my test data ready to go. I had to do something tricky here. The size of the test data is, I can't remember, is it 1.8 million or something?
It's 18 million, and I learned this the hard way because
Oh yeah.
This is at the very end of the notebook.
Yeah,
and
you've run this far and it bombs, all right? So you've run for hours.
predict on it and boom, out of memory, and then you have to restart the whole notebook again.
So I ran into that problem too. But what I determined was, at this point you're not doing any training, so it doesn't have to see all the data at once, right?
Yep.
So I partitioned the data. I broke it in. It worked out that I could break it into 3 parts and do training, or doing the predictions for each of the 3 parts separately. And that way I wouldn't run into this problem, right? So it's 18, let's see, what is it? Yeah, 18.7 million. But I broke it up into 3s, and then it fit into actual memory and ran. So I did this, you can see this repeated for each prediction 2, and finally for prediction 3. And now I'm going to append them together, 1 and 2, and then that result to 3 and get the full shape. And you can see back here, I looked at, here's my full shape and here's my prediction. So I'm back to the original size now, and I didn't run out of memory. And then I submitted it.
I like how you submitted it. It's very interesting to me.
Oh, sorry. Yeah. What's interesting about it?
Because you took the sample submission file.
Oh yeah.
You kept the index as it is, the click ID, and you just entered your own is attributed.
Oh yeah. The Kaggle competitions is not my first go around. I've seen many people do this. So normally they will give you a sample submission that gives you the structure, but they also put the real IDs in there.
Mm-hmm.
In this case, I think it was like the click IDs, right?
Yeah.
So these will be the same as what are in the test file.
Yeah.
So as long as you didn't mess up the order going in,
exactly,
it matches up, and you can all you can do is just replace the is attributed with your predictions.
That's what I was about to say. As long as you didn't mess up the order, you didn't shuffle somewhere, you should be okay.
Yeah.
I was keeping track of somebody.
Okay. Okay.
Thank you. I was keeping track of click IDs and these attributed separately and was combining them, and that was taking a lot of time. But yeah, once I saw this solution, I was like, okay, this is very interesting. You don't even keeping track of click IDs, you're just appending them to the submission file.
Right. I have seen some competitions where they don't give you a sample submission. They just describe what it should be, and then you have to do the hard work.
Oh, okay.
Yeah.
For splitting the test set, it would be nice if there was some kind of feature that says, okay, you can't really fit this in your memory. It would be nice to.
If they told you that up front.
Yeah, because I mean, you learn the hard way. It's the
Well,
very end of your notebook, and then it crashes. Like, what in the world?
maybe it's real life, right? So yeah, when I ran these, I got not quite as good as George. Pretty close. I didn't have to do all the work he did with feature selection.
But I'm still surprised that my baseline model with just the
That's so
label
much better.
encoding for those 5 categorical features is the best, and it was tree based. Like,
Apparently, label encoding is the way to go. It's like,
but I don't know. I mean, I mean, this is why I love this session. This is probably one of my favorite one, and I'm glad we postponed it from last week because I really got last week and took a deeper dive. I was like, okay, cat boost, target encoding, counter coding. You have to improve it by a little bit. And I went the opposite way. I was getting worse results. I was like, what am I doing wrong?
yeah. I mean, I will say for the deep neural network people that these kind of things, you can imagine if you were writing your model from scratch, right? And you would have to have an input coming in, and then an embedding layer, a TensorFlow embedding layer, and then feed that into whatever next you had the dense. You'd have to do this over and over in different ways. It would this saves so much time for that kind of work.
I will take your notebook and I'll explore these embeddings. I'm curious how they relate to some kind of other encodings. Are they close to like maybe like a count encoding? Are they close to maybe a label encoding? I don't know. I'm curious what they look like.
I don't think they are. I think they're much more like, if you think more like an NLP or something, they're a learned embedding for that number. Because if you think about NLP, the sequence coming in is just a number, right?
Mm-hmm.
That you then learn an embedding for. And this is just a number that represents the string that's in the category,
Mm-hmm.
and you're learning an embedding for it, right? So it's
very
similar. Sometimes this is called entity embedding. If you've ever heard that term, the concept is called. So if you look up entity embedding, that's.
Is there anything like this outside of TensorFlow, like maybe in sklearn? I haven't seen this. Is there a concept like learn embedding in sklearn? Does anybody know? I don't know. Or is this just a TF TensorFlow feature?
I'm sure a lot of deep neural networks do this. Not just. I'm sure that you can do this with PyTorch too, but maybe not as elegantly. But you certainly can do it.
Saying, what about sklearn? Do you think you can find it there? I have to look.
I'm not sure there's really a need. I mean, the tree-based learning, handling category columns is.
It's almost like a learned embedding, right? It's a learned encoding. Sorry.
This is a learned encoding, yeah.
Yeah. So I'm curious if there is a learned encoding capability in sklearn.
Yeah, I think it's also possible. I don't know if they support this in this part of, with this feature column here, with this embedding column. But, just like in natural language, if your categories, say your categories were codes for something else, you might bring in some like learned embeddings from that you use some other model to learn with, right? So just like in NLP, you can bring in like embeddings from BERT, right?
Yeah.
Where they've trained on some other data set. You could do the same thing here. You could bring, if these categories came from some other world, somewhere you had more data around the categories, you could train embeddings there and then plug them in here, right?
Yep.
Just like you do in NLP.
Awesome. I like this, and thanks for sharing your notebook, David. I learned a lot.
Sure.
Cool. All All right, friends, let me just share my screen real quick and we're going to wrap up. So I enjoyed this week's session because it also introduced me to some features of Pandas that I hadn't seen before. One of them was query. I like this capability to basically filter or query your data frame based on just more human-friendly expressions. So instead of doing something like give me everything where a column is equal to another column, you just do it based on the column names. It's a little bit more easier to read. Another one was assign. So all you're doing here is actually creating a new feature for your data frame and you're assigning it at the same time. So you can also do it with two at a time. Basically, you're creating a new feature or a new column in your data frame, and you're using it later in this almost looking like a Lambda function. So then your data frame would look like this with the two new features. Another feature that I liked was this.
With assign, could you use multiple columns to build a new column? Like, I think you can, right?
Yeah, so here you're creating a new one based on an existing one, then a new one based on the one that you just created. So yeah, it's
But what I mean is, like, if your temp F was based on not only temp C, but maybe it was multiplied by temp D or something. I don't know.
it's a function. Yeah, you can go as deep as you want here.
So this is where you could do like really quick feature engineering.
Yeah, I liked it. Another one was factorize. Let me remember what that was. Oh, I think this was some kind of encoding. Encode the object as an enumerated type or categorical variable. I don't remember where we used it, but I saw it in one of the courses, one of the exercises. Another one was reindex. We used that in the rolling, I think, when we're trying to calculate if a Kickstarter project, how many projects were taking place for the last 7 days. So what that does is, it's a very neat feature in Pandas. So let's say you have a data frame of HTTP status, response time, and your index is different browsers. And let's say you introduce a new index with some new browsers. I don't know if anybody uses or these are made up. It looks like made up. When you do your original data frame reindex the new index, you're basically telling your data frame, okay, keep the original data, but also introduce these new indexes, and you don't have any values, so they're going to show up as any. Trying to remember what happened to this guy. Oh, sorry, they were dropped, right? So your new index is basically a collection of your previous index as well as some new ones. There were no values for the new index, they're going to show up as NA. You can fill those NAs with 0. You can fill them with a string. You can also reindex based on columns. You're basically introducing a new column, and that will show up as NA because it was not in your previous data frame. Let's see what else you can do. You can I think you can do some kind of let's see here. I think you can. I'm trying to remember here. So I think this is where you were looking at the previous values. So let's see. 100, 101. I don't remember, but there were some interesting features here that I find really interesting here, and you could also.
It was useful when they wanted to join things that had different indexes, right? So they replaced one of the indexes with the other, and then they could do a join.
Yeah. Diff was used as well, the difference between one element and the other. So let's say you have, this is your data frame. This one is increasing by 1, column A, column B is increasing by 1 and then 2 and then maybe another value, and you can see here the differences. You can also do differences across columns. You can do differences across or from 3 rows above or from a row below. So that's interesting. Rolling was also another interesting calculation. We did the 7-day rolling or 6-hour rolling. Oh, it reminds me of the SQL operators you do, like a window functions. Expanding. So this is our original data frame, 0 to 4, and you're expanding it by 2. I'm trying to remember what you're doing here, and you're taking a sum. So you're taking a sum of 0 to 1, which is 1, but you're only starting it from 2. Then the sum of 2, 3, NA is 3, 4 is 7. Don't remember where we used this, but it was useful, I think. Another thing that was mentioned in the exercise was this Peruda pi. I didn't get the chance to explore it in detail. I don't know, have you seen it before, David? It looks like another one, like a feature selection method. So we saw, right? We saw the univariate one. We saw the L1. This looks like another one. Cool. All right, then we'll end up with just a note that next week we have delving into SQL. So if SQL is of interest to you, please join us. We have an introduction to SQL session on Wednesday, and then on Friday an advanced one. Later on, we have data cleaning and geospatial analysis, and then we have even more sessions coming up. Cool, friends. With that said, I want to thank everyone. Thanks for joining. Thank you, David. Thank you, Robert, for your valuable input. This was very useful, and I'll see you next week.
Yeah, thanks, guys. Thanks a
Bye,
lot.
everyone. Bye,
Thank you very much. Have a nice weekend.
Have a nice weekend, everyone. Bye-bye.
Thank you, guys.
Thank you.